Hi, my name is Ui-Hwan Kim, and I'm going to describe how to leverage both dense correspondence and miscorrespondence to achieve robust change detection with imperfect matches. Firstly, what is scene change detection? It is the task of localizing changes and identifying change categories given two scenes. For example, given reference and query images taken at different time steps, we want to evaluate the change masks. And there are numerous applications such as surveillance, anomaly detection, and maintenance. However, previous works have too small data set to represent real-world characteristics. Another limitation is they assume perfect matches which are not plausible in the real-world scenarios. And our research goal is to achieve robust scene change detection with imperfect matches by leveraging both dense correspondence and miscorrespondence. More specifically, we want to receive reference and query images taken at different time steps and with large viewpoint difference. And we are going to evaluate change maps. And we are going to do this by evaluating scene flow estimation. This is another view of our research goal. By receiving reference and query images, we are going to design a network, and we are going to evaluate scene flow, which is correspondence map, and change mask, which is miscorrespondence map. Our simultaneous scene flow estimation and change detection architecture have four major components. And the first component is two-stream feature pyramid. It enables correspondence and miscorrespondence estimation in any image resolution, and it consists of 4 levels. Another thing is correlation layers. It evaluates global correlation and local correlations, which are used to evaluate correspondence and miscorrespondence maps. And correspondence map decoder receives the correlations evaluated in the previous step to decode the correspondence map. And the miscorrespondence map detects change masks. And to train our network, rather than gathering extra annotations, we made up our data set. More specifically, from any reference image, we firstly conduct random image warping to make query images, and then we perform copy-paste to add this kind of random images, random objects, and this could make change masks. So we do not need any extra annotation. However, we can use any image datasets to generate training samples. And this is comparative study results. Our method are robust to large viewpoint difference and robust to environment variations. Thus, our method outperforms the baselines by a large margin, like this. This is qualitative comparison result. Given reference and query images taken at different time steps, previous works do not robustly detect changes, whereas our method could detect changes robustly. And in the case of dusty air, where reference and query images have different environmental features, previous method could not hardly detect changes, whereas our method could detect changes robustly. This is quantitative results on different data sets. And on these data sets, the evaluation results shows similar trend. And this is qualitative study results. As before, our method outperforms baselines. The limitation of our work is that our work assumes given pairs have at least a slight overlap. However, SIMSEC could learn to distinguish relevant pairs. And our SIMSEC network is robust to viewpoint difference and environmental variation. And we carefully designed the training scheme so no extra labels are required. We collected a test benchmark data set for evaluating change detection algorithms placed within real-world applications. For more details, you could visit our GitHub and you can retrieve the test benchmark data set. Thank you for listening.